Greetings. This is going to be the first video lecture that you'll be seeing in this course. And what we're going to do today is talk a little bit about circuits and their goal of transferring electrical energy through charge. So we're going to be talking about how a circuit operates in the sense of how it moves electrical energy from one place to another. And we're going to be using that as a framework for understanding that the transfer of electrical energy really is the reason that circuits exist, is to move electrical energy, say from a battery in which it's stored chemically, to a motor in which the energy is then transferred to mechanical energy. So the idea is that we want to do something useful through the transfer of energy. So what is a circuit? There's a couple of things we need to talk about when we're trying to understand what exactly a circuit is. The first thing is that it is a closed path. So it is a closed path that electricity can flow from one end all around the circuit and back to where it started from. So the key there is that it has to go back. Electricity flows, and we'll be talking about what exactly that means throughout this video. And it transfers electrical energy. So this is the framework that I want you to always consider when you're thinking about what is the circuit doing. The question you need to ask yourself at all times is, where is the energy moving from? Where is it moving to? And what is the point of moving that energy? Why am I doing that? And this is the more general term, is that it does something useful. So you've already had some experience with electric circuits, even if you've never built one before. So you flick the light switch, for example, which transfers electrical energy from the power station into your lights. And what's being useful there is that now you can see. You can see in your darkened room because you've transferred that electrical energy from one place to another, and that's something useful is the fact you can see. I'm presenting right now on a laptop. The battery is storing chemical energy, transferring that into electrical energy, and all of the different processes in this laptop are governed by circuits, and the something useful that I'm doing is producing a video for you to better understand circuits. So once again, I'm going to reiterate, the key to understanding circuits is to understand that they transfer electrical energy in order to achieve something useful. And I'll just leave this slide up again. This is that key idea that I've been talking about. So the next thing, I just want to show you an example of this, and this is a motor being moved by a battery. So we're transferring that electrical energy from the battery into the motor, and then the motor is transforming that energy again into mechanical energy. Now, a reasonable question we might ask is, okay, energy has been transferred, but by what? And you may have heard of the electron or electric charge in general. And the electric charge, and specifically the electron in this course, is what we're going to be assuming the energy is transferred by. So there are some subtleties to that I will leave to physicists and I will leave to future courses. But for our purposes, we have the idea that electric charge is transferred by electrons. So electrons gain energy from sources. And sources are things that you've seen before. They're batteries, they're wall outlets, or solar cells, or generators, and that sort of thing. So energy increases at a source. Oops. And then they give energy, or they lose energy, to loads. And loads, again, are things you may be familiar with, things like light bulbs and smartphones. So they lose energy when they go through a load, and they lose that energy, they typically transfer it into the load, and the load does something desirable. For example, once again, turns on a light, moves a motor, that sort of thing. In between, what we might call the circuit elements is the control stuff. So it's not enough to just take a battery and connect it to your load. Sometimes you might need to regulate the voltage. You might need to regulate how much energy goes into that load. You might need to regulate how quickly that energy goes into the load, or how quickly it goes away from the load, that sort of thing. And that's the elements like switches or resistors you're going to talk about quite a bit in this course. Energy storage elements, all those sorts of things that we're going to be exploring more in this course help to control that flow of energy from the source to the load, where the load is the thing that is doing something useful. Now, when we're talking about the electron, electrons are extremely numerous and they're very difficult to talk about. So in this course, we'll be introducing quite a few additional units, and one of those units is the coulomb. We can't reasonably talk about, say, 10 to the power of 20 electrons. That's just a difficult and clumsy thing to do. And it makes it so that our discussions go off into these mathematical formalisms that aren't very conducive to learning about how to work with circuits. So instead what we do is we introduce a unit called the coulomb. And the coulomb is just a useful unit of charge. And 1 coulomb right here is quite a large number of electrons, 6.24 times 10 to the 18. The exact number, so why is it this? It comes from electromagnetic theory. And I won't dwell too much on that, but the number is not arbitrary. So the amount of force, basically, that electrons can produce through a particular type of setup is how the coulomb is defined. So again, it's not just a random number. It does, in fact, come from electromagnetic theory. In this course, we don't focus too much on that, but I do want you to just walk away from this video understanding that there is actually a reason for this seemingly random number. What's key, though, is that coulombs make it easier to work with the numbers involved. I'm no longer having to use very difficult language like 6.24 times 10 to the 18. I can just say 1 coulomb. I can talk about it in terms of smaller numbers, and I can start defining other units based on that. That being said, the electron on its own is not very useful for discussing how energy is transferred in a circuit. Electrons are the carrier of that energy, perhaps we might say, but we wouldn't necessarily be too concerned about the energy of an individual electron if we're not talking also about how it moves through the circuit. So going back to that original definition, electricity has to flow. It can't just stay there statically. And so the next thing we have to talk about is time. How does this charge flow in the circuit? How does it move, and how do we measure that movement? To do that, we introduce a new unit called the ampere, or the amp. You'll hear very, very commonly they're known as an amp, which is short for ampere. And this is how electricity flows. So charge, like I said, on its own is not very useful. There are some times in which we will be using just charge, but the fact that charge is moving and has energy through movement is really what we're concerned about. So the number of electrons per unit time is really what's important in many of our discussions. So this is the ampere, and it's defined as 1 coulomb per 1 second. And this is known as electric current. So you're going to see this a lot. An electric current is the flow of electrons. So let me just write that down. Okay, so electric current is the flow of electrons. Now, a reasonable question is, well, through what? What is it flowing through? And this answer is a little bit abstract, so we're going to talk about circuit elements, and we're going to start asking ourselves, well, what does that mean? So when electricity flows through a circuit, what's really going on there? Typically, we denote charge through a circuit element as Q of T. And I'm using the generic term circuit element rather than a specific term like a light bulb or a battery, because I want to make it very clear that when we're talking about charge flowing through a circuit, it doesn't matter what it's flowing through. It doesn't matter that it's a light bulb compared to a battery. The charge is still moving through it in a very similar way. So if 1 ampere of current is going through a light bulb, it doesn't flow through it differently than if 1 ampere is going through a battery. So Q of T is a very standard notation for the charge as a function of time. And now let's think about what exactly that flow might mean. So every circuit, whether it's something large like a power station or it's something very tiny like in my watch, all of them are connected via some kind of wire. So I think that the one thing we can talk about that is universal to all circuits is that the concept of wire, conductivity, and connecting conductors. So let's take a look at a wire. Let's pretend as though we're zooming in directly onto this onto the wire, and what we will see is essentially a cylinder of metal for the most part, right? So what does a wire look like? Well, it might look like that. So this is a zoomed in piece of a wire. And now when we say that 1 coulomb per second is flowing through it, what we mean, take a look at the face here of this wire. So this is the face of the wire, and we mean that electrons are flowing through. So a common thing is just to say E with a negative. And now let's presume that we have some kind of a counter at that face. So at the cylindrical face, electrons are flowing through. What will count as 1 coulomb of electrons per second. So if we were to count every single electron that would move through that face of the wire, we would count 1 coulomb every second. And that's what we mean when we say that it's flowing through. So the key is we need to consider some kind of area. Typically, we call it the cross-sectional area, as though you cut it. And we look at how many electrons per second are flowing through that area. And that's what we mean by current. Now, how do you get current from charge? Luckily, there's a nice definition that follows directly from calculus. So current is the time rate of change of charge. And so this is the definition that we'll be using. Notice that it is a derivative. So I of t, which is a common variable used for current, equals to dq by dt. What's important is this is a derivative, so we consider this to be a continuous quantity. I'll use the shorthand CTS to mean continuous. It's a continuous quantity and it can be differentiated with respect to time, and that produces this flow of current, and the unit is amps. Let's do an example. Let's say that charge is flowing through a wire via this function. So Q of t equals to 3t plus 2 coulombs, where t is in seconds. So we always need to make sure that we're clear on our units. Coulomb is our unit of charge, and t is in seconds, which means that we can directly apply that equation. What is the current through that wire? Well, from before we had that I of t is dq by dt. And taking the derivative here, what we see, if I take the derivative of this linear function, I'll get 3. Equals to 3, what? Coulombs per second, or 3 amps. And that is what we're looking at when we talk about current from charge. We take Q of t, we take its derivative, and now suddenly we have the capacity to talk about the current through the element. It's not common that we'll be talking about charge itself. Almost always we'll be dealing with currents, and then later we'll be dealing with something called voltage. However, it's important to understand that charge is not to be left out of the entire consideration. Charge is what is transferring electrical energy from your sources into your loads and through your control structures. It's not that it's not there, it's just that it's much more instructive and much more informative when we're dealing with the circuit to deal with how that charge is flowing rather than how much charge is there. And that's why we tend to talk about currents. So I hope that was useful to you. In the next video lecture, we'll be talking a little bit about how we know which direction the current is flowing, as well as how much energy that charge gets when it passes through sources and how much it will give away to a load. Thank you.